All right, IB Physics, Ms. Getz here. So this assignment this week is looking at a projectile motion problem. And in our problem, we have this marble that's rolling along a track on a table. So it's gliding along this track. There's negligible force drag, which means negligible air resistance. We can also say friction is negligible too. Negligible means it doesn't matter. And we want to start off by sketching a motion map of the situation. So what this means is that we're saying, okay, well, if the ball starts here, it's going to continue moving forward with like the same velocity each time. And then I expect that the ball will fall sort of like an arc, half of a parabola, and so like that maybe. And so that's the beginning of my motion map, but remember the motion map also includes our vectors for our velocity. So here's our velocity. I'm trying to make it the same size as this arrow with limited success. So we're just continuing with this velocity. Then the velocity starts being a little bit downwards. Ooh. And then it's even a little bit more downwards. And then it's even a little bit more downwards. Wow, okay. So this is our motion map, and it's showing what is happening to the velocity of the ball as it projects, as it flies off of our table here. So now that we know what this motion map is like, we're going to go ahead and take a moment to sketch and label the free body diagram for the marble, both when it is on the rail and off the rail. So I would advise you actually to pause here, pause the video, try drawing this, and then press play when you think you've got your free body diagrams for on the rail and off the rail. And so for my free body diagrams, I know that the marble has a force gravity acting on it downwards the whole time. Force gravity is not going to go away. But when I'm thinking about the marble on the rail, there's that other force from the rail holding the marble up. And that would be a normal force. And that's actually it. The marble doesn't need a force to continue moving this way. It will just keep on doing that because of Newton's first law of motion. Objects in motion, they're going to keep on being in motion. Then when it's off the rail, the table is no longer interacting with it, and so we only have force gravity acting on our marble once it's off the rail. So I've considered my forces, and now my goal is to determine the horizontal range of the marble as it falls to the floor. And I have these steps here to help you solve and explain what you're doing so you can get a sense of how you solve these projectile motion problems. The horizontal range means that we're looking for this distance, the distance away from the table that the marble lands. Range is a word that means distance, and horizontal, means the x direction, so horizontal. And so to do that, we're going to start out with our steps. So our first step is to record our knowns in the x and y direction, and I have some of them already down here for you. So go ahead and pause the video here, pause, and record down what you think the knowns are that you could fill in, and double check that you agree with my knowns in both the x and the y direction. Awesome. So hopefully you've listed that you actually know the initial velocity in the x direction is 10 meters per second. They tell us that in the problem. And you might have recognized that because the acceleration is 0 meters per second squared in the x direction, because there is no F net in the x direction, that means that our acceleration is 0. That means that the velocity is actually staying the same the whole time. 10 meters per second the whole time in the x direction. However, in the y direction, that's not the case. We know that the initial velocity in the y direction is 0 meters per second. And how do you think we know that? How can you think of that? Like, why the velocity up here, I'm going to draw in my x and y components, right when we get off the ramp, when the ball is like right there, the velocity in the y direction is going to be 0 meters per second. So take a moment and explain how you know that. Maybe pause the video. And hopefully you explained something about how the marble doesn't have any initial velocity in the y direction. It's just essentially falling in the y direction. Just like when you let go of an object, it doesn't have an initial velocity, but then it starts accelerating downwards. And hopefully you've also jotted down how you determine the initial velocity in the x direction, which is quite dull because that's just from the problem. Pretty boring. But then we can go ahead, and now that you've done a little bit of explaining, we can move forward to step 2. So we're going to use the y direction to solve for the time it takes the marble to reach the ground. And you might think, well, do I have to use the y direction to do that? And take a moment and consider what you know in the y direction and what you know in the x direction, and why is it that we have to use the y direction to find the time? And so hopefully, pause if you need to, but hopefully you have a description for why the y direction is the direction that's more useful for us here. And I'm going to find an equation that can help me find time from my list of constant acceleration equations. And I happen to see that this one, s equals ut plus 1/2 at squared, has time in it, and it doesn't include the final velocity. How convenient. We don't care about it. The problem doesn't ask us for the final velocity, so I'm not going to worry about trying to find it. So I'm going to solve this equation algebraically for time. And to do that, I actually really like plugging in anything I know that's 0. And I know that the initial velocity is 0, so that means that that whole term is 0. That simplifies my equation to s equals 1/2 at squared. And I'm going to do some algebra to solve for t, so that I get an equation that says t equals. To do that, I'm going to start by multiplying by 2 on both sides. So I have 2s equals at squared. Then I'll divide by a on both sides. 2s divided by a is equal to t squared. And I'm going to go ahead and take the square root of both sides. And get that 2s over a, square root the whole thing, is equal to the time. And so I'm going to go ahead and plug in all of my knowns here, making sure to consider that some of them are negative. What that is telling me is that we have decided, or I have decided for you, that downwards is negative and upwards is positive. The acceleration due to gravity is downwards and we're calling it negative. And so that's why this displacement here is also negative. So go ahead and take a moment to calculate t, our time, using your calculator, writing down your work here. You can solve in this whole area here, it's fine. And hopefully you got, uh-oh, I left that A behind for A. Hopefully you got like 0.55 seconds, 0.5 seconds. So time equals 0.55 seconds. And so that's our time, and so I can write that down here in my knowns table, because now we actually know how much time it takes for the ball to hit the ground. And so then we can move on to step 3 and use the time you found in the y direction to determine the displacement in the x direction, aka the horizontal range. And so you might actually find it helpful to pause and take a moment to do this explain question. Why is the time in the x direction going to be exactly the same as in the y direction? Pause and think about that. Why would I be able to take this time and put it over here? Well, hopefully you thought a little bit about what happens when the ball hits the ground. So when the ball actually comes in contact with the ground, that means that the ground is providing some additional force, changing the ball's motion. So it's causing the ball's motion to stop. And so that means that if it's stopping when it hits the ground is in the y direction, right? Like the ground is here, it's not down here. If it were down lower, that would be a different amount of time. So when the ball hits the ground, it's at the same time in either direction. Like the time is in both directions. Both directions motion is happening simultaneously. So if we know when the motion ends in the y direction, that's also when the motion ends in the x direction. Time is kind of the thing that unites the two directions together. If we know what time it is, we can say where it is in the x direction and where it is in the y direction. So then we can go ahead and find the x displacement. And in fact, if I'm looking for displacement, I'm going to use that same equation, ut plus 1/2 at squared that I used before. And I'm going to plug in, again, that we know something is equal to 0. And that is this acceleration in the x direction is equal to 0. So this part goes away. And now I have an equation that says s is equal to ut. And I can go ahead and plug in our initial velocity and our time and get something like 5.5 meters away. And you can kind of pause and be like, does that make sense? The ball is going 10 meters per second, and I'll actually tell you 10 meters per second is like 22 miles per hour. If a thing is going 22 miles per hour, does it make sense that it would be like 5 meters away when it lands from like kind of a tall table? That's pretty fast. So I'm going to say it does make sense. It seems pretty reasonable. And I'm going to go ahead and box my answer. So you can decide to just turn in this whole paper as 6.3. Or if you would like to really extend your learning and really work on doing this thing called projectile motion, I have some mild, medium, spicy problems attached to this assignment that you can try out, and you can pick as many of them as you would like, get some extra credit if you want, and really try doing this same process where you're setting up the x and the y direction to try to solve your problem. On almost all of these, in fact, not on almost, on all of these, in the x direction, you don't have any acceleration. You would only have acceleration in the x direction if you had like a jetpack on or something, and we're not going to be dealing with that in these problems. So projectile motion is all about when we just have acceleration in the y direction, how can we figure out maybe where the object is, or how long it takes to get somewhere, or will it collide with something? And so there's lots of different types of these problems. But take a little time and try a few of them out if you have the time, and if you don't, just go ahead and turn in this problem you've just solved on this graphic organizer. Good luck, and keep me posted on any questions you have.